Hello there, Mr. Sutton here, bringing you the Algebra 2 5-3 lesson on graphing radical functions. This is going to be a two-parter. In this one specifically, we're going to be graphing even and odd radical functions, and also writing functions for transformations of radical functions. And if you're doing this as part of the honors lesson, as an extra thing, we're going to be using radical functions to graph parabolas and circles. To start this one off, I've given you the square root function here and a table of some x values. Pause the video and take a moment to complete this table, and then using that and perhaps some technology, see if you can graph out what the square root function looks like. Once you take a look at the picture, see if you can figure out the domain and the range. So pause the video, give that a shot. Alright, so plugging each of these items into the square root of x, square root of 0 is 0, square root of 1 is 1, and you probably figured out why I picked 4 as my next x value instead of 2. The square root of 4 is a nice whole number, namely 2. Alright, so let's put this on a graph. So we've got 0, 0, 1, 1, and 4, 2. And before we connect these dots, let's go ahead to Desmos and see what this thing actually is shaped like. So we've got f of x equals, and then I'm going to write in sqrt just for normal square root of x. And just zooming in a little bit, we see basically where we had some of those dots. But one interesting thing is, if you zoom out a bit, this thing goes seemingly forever to the right, but we've got this endpoint here at 0, 0. So let's graph that shape. So we endpoint at 0, 0, and then going forever to the right. Now what's going on with this endpoint, think about what would happen if you tried to plug in -1 for the square root. So you'd get an imaginary number which you cannot graph on the xy axis. So that's why we have to stop at 0, because any of the negative numbers aren't going to work out for us. So that actually gives us a domain of x greater than or equal to 0. Can only plug in 0 or positive numbers. Now let's look at the range, the y values. We see that there's nothing below the x-axis here. And this makes sense because if you're only allowed to plug in 0 or positive numbers, then the only thing the square root can give you back are 0 and positive numbers. So the range, it turns out, because of the domain, the range is also going to be greater than or equal to 0. Y greater than or equal to 0 in this case. Now one other thing I wanted to show you real quick here. This was square root, and the title of this slide was even root functions. And we know that square root is not the only even root. So let's go back to Desmos and take a look at what happens if I graph some of the other roots. Let's do another one, and this time I'm going to do fourth root. So we'll write in nth root, and I'll put a 4 up here and an x, and there is the fourth root. So fourth root looks kind of like square root, but it grows even more slowly. And if we keep going, let's do the sixth root. So we've got 6 and x, and we see that that one's growing even more slowly than the fourth root. But all of these roots are ending at 0, 0 because you can't take an even root of any negative number. So in general, all even root parent functions are going to have this same domain and range. So we're going to treat them all kind of equivalently when we turn around and try to graph these transformations. So we're going to do our first example trying to graph a transformation of the square root function. And our process for these transformations is going to be exactly what it was when we did lines, quadratics, and polynomials. Namely, we're going to start by figuring out kind of in words what this transformation is doing. Then we're going to write out the parent function table with those key points in it that we just saw on that last page. Then we'll write out some new rules for x and y based off these transformations. And then we'll just refigure out those points and graph it out. So we'll do the first part together, figuring out what this is doing. Now, just as a little bit of review, stuff that happens inside the function, like this -3, this is a horizontal change, and it's going to be opposite of what it looks like. Stuff that happens outside the function is a vertical change, and it does exactly what it looks like it's doing. And when we're doing adding and subtracting, that's a translation. Multiplying by numbers and negatives, that's all kind of stuff that gives us stretches and reflections. So in this case, this -3 inside means we are going 3 to the right, and the +4 outside means we're going up 4. So this is a translation right 3 and up 4. Pause the video and see if you can figure out the rest of the steps on graphing out this transformation. Okay, so our next step, we're going to write out our square root of x parent table. That was again 0, 0, 1, 1, and 4, 2. Those were the most helpful points. And it turns out all the different roots actually have 0, 0, and 1, 1 in them. So it's really just this third one you have to kind of remember or plug in. So now what are we going to do in light of these transformations here? If we're going right 3, that means we have to add 3 to the x values, so x plus 3. And then if we're going up 4, that means we have to do y plus 4. So let's go through and apply that to each of our values here. So I'll do the x's first. 0 plus 3 is 3, 1 plus 3 is 4, and 4 plus 3 is 7. Now adding 4 to all the y values, we have 4, 5, and 2 plus 4 gives us 6. All right, so putting that all on a graph now, I've got 3, 4, that is right here. We've got 4, 5, and we have 7, 6 is up here. Now this is part of where you need to know kind of the shape of this square root function. Remember, it has that one endpoint, and then it goes forever in the other direction. So where did the endpoint move to? The quick way to see that is to see what this 0, 0, which was the original endpoint, what did that turn into? Well, that turned into 3, 4. So 3, 4 is our new endpoint, so we're starting here and going through these other points. This next example is for the CP non-honors version of the course only. So if you're taking the honors version, you can skip on ahead to the next example. Doing the CP version, we'll do this one together. Pause the video and see if you can graph this one out. All right, so the transformation happening, since we are multiplying inside, it's going to be a stretch or a shrink, and it's going to be opposite of what it looks like. So since we're multiplying by something less than 1, this is actually a horizontal stretch. We're actually multiplying by 4, whatever the x values are. So let me write my parent table again. This was my 0, 0, 1, 1, and 4, 2, like we've been doing. And now for the new x values, we're going to be going 4 times the x values for this one. And then for the y values, there's nothing happening outside this function, so those just stay the same. And now going through and changing all my y values, 4 times 0 is 0, 4 times 1 is 4, and 4 times 4 is 16. And the y values are still going to be 0, 1, and 2. So in order to graph this out, I'm going to need to leave enough space to fit 16 on my x-axis. So I'm going to make my x grid lines go by 2s. That'll let me get everywhere I need to go. So we've got 0, 0, 4, 1 is right here. And then we've got 16, 2 right up here. And then graph through those. For this problem, we took basically all the things we could do to make these problems trickier and threw it all in one place. So there's all sorts of craziness going on here. We've got this 1/4 power. We've got a whole bunch of other transformations going on. So how do we even get started on this? Well, one thing that we know about these fractional exponents is that these are really radicals in disguise. This is really the 4th root of whatever it's being applied to raised to the first power. So whenever you see these fractional exponents, I would start by rewriting it as a radical so that you're a little more comfortable kind of using what we've already done to graph it. So in this case, we can call this 2 times the 4th root of x plus 5, all of that minus 4. And this is what we're actually going to be graphing now. And of course, if we had the 1/2 power, that would be square root. So you can do this with any fractional exponent. Next up, what are the transformations going on here? So don't worry so much about what we do with this 4th root just yet. Just look at the other transformations. Pause the video real quick and see if you can figure out what's going on. So we've got a few things. We've got this 2 outside, which is going to give us a vertical stretch. And the plus 5 inside and a negative 4 outside means we're shifting left 5 and down 4. So vertical stretch and translation left 5 and down 4. All right, so now it's time to make a parent function table for x to the 4th. Or not x to the 4th, the 4th root of x. How do we do that? We have the parent table function for the square root function already. So how do we generate one for the 4th root, or really any even root? Because we want to kind of have a way of doing it for everything. So all of the even nth root parent tables, so 4th root, 6th root, 8th root, and square root, all of them, they're going to have the following points. Just like square root, this one is going to have 0, 0, and 1, 1. And you can very quickly verify that the 4th root of 0 is 0 and the 4th root of 1 is 1. But now how about that third point? For the square root, that was 4, 2. The reason I chose 4 is because 4 was a perfect square. So when I square rooted it, I would get a nice whole number. So in this case, I'm going to want to pick something that's a perfect 4th power so that when I take the 4th root, I get a nice whole number. And how about we just pick the lowest perfect 4th power we can get? That would be whatever 2 to the 4th is. So in general, you're going to want that last point to be 2 to whatever that index is as a power. That'll guarantee that when you take its nth root, you just get 2 back, a nice easy whole number. So pause the video, see if you can figure out what that third point should be, and then do all the rest of the things to graph this out. All right, so we've got 0, 0, 1, 1, and 2 to the 4th would be 16. So I'm also going to have 16, 2 as my third point. Now for transforming this for my g function here, for the x's, we're only shifting left 5 in terms of horizontal stuff. So I'm going to write x minus 5 for that. For the vertical stuff, we're multiplying the y values by this 2 out here, and then we're subtracting 4 from that. So 2y minus 4. Now we're going to go through and change all this. So 0 minus 5 is negative 5, 1 minus 5 is negative 4, 16 minus 5 is 11, so those are going to be interesting to work with. And then over here, 2 times 0 minus 4 is negative 4, 2 times 1 minus 4 is negative 2, and 2 times 2 minus 4 is just 0. So I need to leave enough room to go from negative 5 to 11. So at the very least, my x grid lines are probably going to have to go by 2's. The y's, we don't really need to worry as much about those. So going by 2's on the x's and 1's on the y's, first point was negative 5, which is right here, comma negative 4 down here. And then we have negative 4, comma negative 2. And finally, all the way over here, we have 11, comma 0 on the x-axis. The end point that was 0, 0 is now negative 5, comma negative 4. That's this point right here. So starting here, we're going to go through those other points to get our 4th root function. So at this point, if you're doing the CP non-honors course, this is the end of part 1 for you. You can pause the video and have some fun graphing these even-rooted radical functions. If you're doing the honors, we're going to keep going through the odds. Welcome back, whether you are continuing on with the honors or rejoining us from the CP course. We're going to move on to these odd root functions now, and we'll start this the same way as we did the even root functions, just kind of getting the lay of the land with a basic parent function. If it worked once, why not again, right? So here is a table that you will find helpful for doing the cube root of x, and I might as well let the cat out of the proverbial bag here and tell you how I picked these x values. These are all perfect cubes, so they will be easy to plug into this function and get nice whole numbers. So do the same thing you did with the even roots. Complete the table, graph it out, check it with Desmos, and then figure out the domain and the range. Go for it. All right, so taking the cube root of each of these, cube root of negative 8 is negative 2, cube root of negative 1 is negative 1, 0 is still 0, cube root of 1 is 1, and the cube root of 8 is 2, positive 2. Graphing all that out, we've got, let's see here, negative 8 comma negative 2 down here. And I had to make my grid lines go by 2's on the x-axis because I'm going from negative 8 to 8. And now our next one, we have negative 1 comma negative 1 right here. Then 0, 0, 1, 1, tight quarters in here. And then we have 8 comma 2 all the way over here. Let me go to Desmos and make sure there's no unpleasant surprises when I graph this out. So here we are on Desmos. We'll do f of x equals, and then let me do, I can actually write in CBRT for cube root, and that'll give me cube root without having to go through the nth root sort of thing. And taking a look at the graph, this does look basically like what we were about to draw. There's no endpoints here. That's the key thing. So graphing through here, this is our parent function, our parent cube root. And taking a look at the domain on this, we're going left and right forever. So that's going to be all real numbers for the domain. And for the y values, this climbs very slowly. But if you do check this out and you zoom out far enough, you can eventually get up to whatever y value you need to. You would just get there very, very slowly. So this one is going to be all reals for the range as well. And let's just take a look at some other odd-rooted functions. So back at Desmos, let me see here. Let me zoom in a little bit so you can see it better. And let's do fifth root. So I'll do nth root, and then put a 5 up here and an x. And we see it's basically the same shape as cube root, just a little more squished together. And it probably won't surprise anybody. Let me do a different function name here. So nth root, let me do 7th root of x. And again, same kind of shape. It's sort of like an S almost. So it turns out then that all of the odd root parent functions are going to have the all reals domain and range. And this also makes sense when you think about this versus the even roots. With the even roots, we had to stop at 0 because you can't take the even root of a negative number. But with odd roots, you can get an odd number by multiplying, or you can get a negative number by multiplying negatives together. So we can plug in any x value we want for the odd roots, and because of that, we're allowed to get any y value as long as we plug in a high enough number. Without any further ado, we're going to graph some of these odd root functions. So pause the video and see what you can do with this one. And remember, we're doing the same exact thing we did with the even roots. The only key difference here is that our parent table is going to have 5 points instead of 3, and there's no endpoint. Give it a shot. All right, so just like before, let me figure out what's going on with this transformation. The plus 4 inside is a shift left of 4. Minus 5 gets us down 5 for that translation. So left 4, down 5 is what's happening with this. Here's my cube root parent table. Again, we're going -8, -1, 0, 1, 8 for the x values, and then -2, -1, 0, 1, 2 for the y values. So for my new rules for my g function, since we're going left 4, we're going to have x minus 4. Down 5 means we're going to have y minus 5. So we've got -8 minus 4 is -12. -1 becomes -5. 0 becomes -4. 1 minus 4 is -3. And 8 minus 4 is 4. For the y values, we have -2 minus 5 is -7. -1 becomes -6. 0 is now -5. 1 minus 5 is -4. And 2 minus 5, -3. So let me plug all this in on my graph. And I'm going from -12 to 4. So again, my x grid line's probably going by 2s. So we've got -12 comma -7 all the way down here. And then -5 is right here. -6 is down there. Now we've got -4 comma -5. And then -3, -4 is right here. So those middle 3 points are always kind of close together. Kind of looks like Orion's belt a little bit. And then we've got all the way over here 4 comma -3. And then I do my little weird S shape through all that. For this next problem, if you're taking the CP version of the course, we're going to get a little bit of extra practice here. If you're doing the honors version, you can continue on to the next example. So CP version, pause the video and try this one out. All right, so this -3 outside the function is doing two things. The 3 itself is giving us a vertical stretch, and the negative piece is giving us a vertical reflection. So vertical reflection and a stretch. So here's my parent table again, same as last time, -8, -2, and all of our other friends that we're getting familiar with. Now for the g function, this time around, the x's are not changing at all, nothing happening horizontally, but for the y values, we're multiplying all those by -3. So I've got all my original x values, -8, -1, 0, 1, and 8. For my y values, we have -3 times -2, that's going to be 6. -1 becomes 3. 0 is still 0. 1 becomes -1, or -3 rather. 2 becomes -6. So putting all that on my graph, going from left to right, we have -8, 6 up here, -1, 3 right there, 0, 0, 1 comma negative 3, and finally 8 comma negative 6. And then we'll draw the curve through all of those. Beautiful. For this next problem, we're going to give you a fifth root just so we can explore something higher than cube root and get you a little more practice with the basic mechanics. So first off, what transformation is happening with this 2x in here? We'll do this part together. So that is going to be horizontal because it's inside and it's opposite of what we expect. Multiplication means we have a stretch or a shrink. So this is a horizontal shrink. We're specifically going to be shrinking it by 1/2. And let's get our table here, the fifth root of x table. Now to get this, we're going to follow a similar line of reasoning that we did with the fourth root table, only including a few more points because it's an odd function. So all of the odd nth root parent tables will have the following points. All the root tables have 0, 0. That's with everyone. Now instead of having just 1 comma 1, we're going to have plus or minus 1 comma plus or minus 1. So negative 1, and positive 1, positive 1. And just like with the even roots, we had 2 to the n comma 2. Here we're going to have plus or minus 2 to the n comma plus or minus 2. So with this in mind, see if you can build your own parent table for fifth root of x, and then apply your transformations to see what this thing looks like. All right, so here's our parent table. 2 to the n in this case means 2 to the fifth. So that's going to be 32, and the first one's going to be negative 32. Fifth root of that is just negative 2. Then we have negative 1, 0, 0, 1, 1, and positive 32, comma 2. For the transformations to get the h function, horizontally, we said we're shrinking this by 1/2, so 1/2 x. There's nothing happening outside, so there's no vertical change. We just reuse the y values. So multiplying 1/2 times my x values, I've got negative 16, negative 1/2 or 0.5. 0 is still 0. 1 becomes 0.5 and 32 becomes 16. For the y values, we're keeping negative 2, negative 1, 0, 1, and 2, because again, nothing changed there. Graphing all this, if I'm going from negative 16 to 16, I'm going to need to make my grid lines go by even more than I did before. I'm going to make these go by 4s so that I can fit all of that. So we've got negative 16 comma negative 2, which is right here. And then negative 0.5 is going to be hard to do, but it's like an eighth of a grid line here. So somewhere in here, comma negative 1. So pretty close to the y-axis. I can actually move that in even further. All right, so let me move it over to there. There we go. And we've got 0, 0 right there. 0.5 comma 1, pretty close to the y-axis up here. And 16 comma 2 right there. And then let me grab this through all of these points. There we go. All done. For this problem, they want us to write a rule for what the f of x function is going to turn into after these transformations. We've done these types of problems before. The best way to do these, in my experience, is just to create a new function for each individual transformation and just do it one transformation at a time. So maybe make a g function that does this first one, then an h function that does this next one using the g function. So pause the video and give this one a shot. All right, so if I want a horizontal shrink by a factor of 1/6, that means I need to do 6 times the input. So I'll make a g function that has f of 6x in it. And then actually applying that to the f function, that's just going to be the cube root of 6x. Next up, to go 3 units left, I need to take my g function and basically do x plus 3. It's opposite of what you expect because it's inside. So my h function is just g of x plus 3. Now we got to be careful here. The g function takes whatever you plug into it and does this to it. It multiplies it by 6 and then cube roots it. So I'm going to rewrite this then as the cube root of 6 times this new input of x plus 3. And if I want to simplify that, I can make this cube root of 6x plus 18. So this example marks the end of the whole lesson. If you're doing the non-honors CP version of the course, you can stop things here and try out some homework on odd roots along with writing functions. If you're doing the honors course, this is the end of part 1 for you. We have more in store for you in part 2. Join us then. Welcome back. If you're rejoining us from the honors version of the course, we're going to kick things off with a word problem. So we're going to go extraterrestrial for this one. The e of d function below here, 0.25 square root of d, that approximates how long it takes a dropped object to fall d feet on Earth. So for example, a 100-foot drop, square root of 100 is 10. 10 times this would be 2.5 seconds apparently to fall 100 feet. And then the m of d function actually approximates how long it takes to fall on Mars. And if you look at this m of d function, and you're wondering why this problem made it into a lesson on transformations and radical functions, well, we've got a radical function right here in the e function, and the m function is a transformation of the e function. So with all this in mind, pause the video and see if you can figure out how long it takes a dropped object to fall 64 feet on Mars. So let's see how it went. This problem is actually one you could have done if you knew zero about transformations or next to zero about radicals, but it's a cool real-life problem. So if we're plugging 64 into the m function, that means we're doing 1.6 times e of 64. And that really means we're doing 1.6 times 0.25 times the square root of 64. All of that. And you actually could do this without a calculator. Square root of 64 is 8. 8 times 0.25 is going to be 2. 2 is a quarter of 8. And then 2 times 1.6 gives us 3.2. So apparently it takes 3.2 seconds to fall 64 feet on Mars. Good to know. For our next neat little application of radical functions, we are going to use radicals to graph a parabola. Specifically, we're going to graph one of these left-right sort of parabolas. And yeah, there's another way to do this using focus and directrix, but you might prefer this method more. Who knows, just giving you some tools. So the way that this works, first thing we need to do is to isolate the y, so we can actually get this to be like an up-down function. Just remember when you're doing this, you actually need a plus or minus. So pause the video real quick and see if you can get y by itself. Alright, so first step is to multiply by 2 to get rid of that 1/2. And then we'll need to take the square root of both sides. And again, remember, plus or minus when we square root an equation. So we have plus or minus radical 2x. And all we need to do at this point is graph out the positive version of this root, which we've done problems like this. We can handle this no problem. And then once you have that positive version, to get the negative version, you're just going to reflect. Use reflection to graph the negative root. Alright, so pause the video and see if you can graph this out. Alright, so doing this, we have our parent table for square root of x. After all those crazy cube and fifth root ones, this seems like going back to basics. We've got 0, 0, 1, 1, and 4, 2. Don't forget those. And then this 2x here, this is giving us a horizontal shrink. So this is going to be multiplying our x values by 1/2. And then the y values are actually going to stay exactly the same. So our new x values are going to be 0, 1/2, and 2. And then the y values will still be 0, 1, and 2. Graphing all this out, we've got 0, 0, 1/2, 1 is right here, and 2, 2 is up here. And remember, we said that we can just reflect these to get the negative version of all this. So 0, 0 stays where it is. This point here becomes 1/2, negative 1 down here. And 2, 2, we can reflect that to 2, negative 2. And we clearly have a nice sideways parabolic sort of dot pattern here. Let's just finish that up and draw a parabola through it. And we're all done. For this last example, we're going to use radical functions to graph the equation of a circle by basically breaking it into two semicircles, and then they want us to identify the radius and the intercepts, the x and the y intercepts. Alright, so the way to go about this, we're just going to get a couple square root functions out of this. Just like we did with the sideways parabola, we want to isolate y to the first power, so do whatever you need to do to accomplish that. And then we're going to graph that using technology. Again, you're going to get a y equals plus or minus something. This time, I'm going to let you use Desmos to see what it looks like. So pause the video and give that a shot. All right, so first step on this is we would have to subtract the x squared over to the other side. And then after we've done that, to get y truly alone, we have to square root both sides. So we have y equals plus or minus square root of 16 minus x squared. Now, if you don't know what that looks like, that's okay. It's actually going to be a half circle, so if you know how to graph a circle, then you can graph half of that. There's a way to do it, but let's use Desmos for now. So let's see, going to Desmos, let me move this over so I can see the original function. All right, so we have, I'm going to graph out y equals positive square root of 16 minus x squared, and there's what that looks like. It's a semicircle up here. And now I'm going to just cut and paste all this, and I'm going to do y equals negative. Control V, there we go, and there's the lower half of our circle. Beautiful. So there's what we graphed. And just show you real quick, this methodology actually works out pretty well if you have a non-Desmos type of graphing calculator. You have to break it into a positive and negative version. You actually can graph the original here out on Desmos without splitting it up. So let me hide these here, and let's just type it in directly. So x squared plus y squared equals 16, and there we go. See, same as before. But this is a good technique to have just in case your graphing calculator doesn't have that availability of that feature. Anyway, they wanted the radius. So we can clearly see the radius from 0 to any of the four corners here is 4. For the x-intercepts, we've got minus and positive 4. And same thing for the y-intercepts here, plus or minus 4. So that's it for this one. By now you might be thinking that radicals are the root of all evil, but that's not true. It's only the odd ones. The even ones, remember, can't handle negativity at all. Until next time, Mr. Sutton signing off.